Hi everyone, in today's episode we're going to look at the ideal gas law and we're going to see how it was derived. Now the ideal gas law is probably the most important law in all of thermal physics. It's going to come up again and again and again, and it's going to be the basis of what we subsequently go on to discover and find out. So there's an argument to be made that if you're only going to remember one equation in all of thermal physics, this is the one. And when I say we're going to derive it, what I mean is we are going to derive it from other laws that were observed experimentally. We're not going to derive it from what you might call first principles by considering a big box of atoms bouncing about and how they might behave, but rather we're going to look at other things that were discovered experimentally and how those things combine to give the ideal gas law. A little later down the line, once we've done some kinetic theory of gases, we will actually be able to derive this from those first principles, but for now I think it's really interesting to see how it came about. So there are actually three different laws that all combine to give this ideal gas law, and they were all discovered at different times. And what I think is useful to do is to imagine a big box of atoms when we're talking about these laws, and then you kind of get a sense of why these laws are the way they are. So the first law to consider was discovered by the physicist Boyle. It's called Boyles Law. And what Boyle's law tells us is that if we keep the temperature of a gas constant, so at constant temperature, the pressure, written by little p, is proportional to 1 over the volume, written as big V, right? So if you hold the temperature of a gas constant, the bigger you make the volume, the lower the pressure will become. And this is kind of intuitively what we would expect, right? Because the pressure is determined by, if you have, say, a box of molecules, the pressure on one side of the box is done by each time one of those molecules hits the side of the box, it exerts a little force on that side of the box. And if you make this box bigger, then the molecules have further to travel before they hit that side of the box, and the number of molecules hitting that side of the box in every second or every unit time goes down. So as the box gets bigger, you have fewer collisions on the side of the box per unit time, and therefore the pressure falls. So this kind of relationship between pressure and volume, where the pressure is the inverse of the volume, is certainly in line what we might expect. And this is called Boyle's Law, right? And that was discovered in, 1662. It was discovered in 1662. So that was discovered absolutely ages ago. Now, the second law we have to talk about is called Charles's Law. And Charles's Law, again, it is a relationship between two variables, in this case, volume and temperature. And what Charles's Law says, that if we hold the pressure of a gas fixed, then the volume of that gas is proportional to the temperature of that gas. So again, if the pressure is fixed, then you have this relationship where as you increase the volume, you increase the temperature of the gas, or if you increase the temperature of the gas, you increase the volume of the gas. Now again, this maybe is a little less obvious, but it is actually exactly in line with what we would expect. So temperature, what temperature really is getting at is how fast the molecules in our gas are traveling. So at a higher temperature, the molecules are traveling faster. At a lower temperature, the molecules are traveling slower. So let's just have a think about this, right? So we've said that pressure, if we've got a box of gas, is the number of collisions per unit time from the molecules on that side of the box. Now, if that pressure is constant, in other words, if the number of collisions on the side of the box stays the same, if we make sure that that stays the same, then if we increase the volume of the box, the molecules have further to travel. And so if we want the number of collisions on the side of the box to stay the same, we've got no other option but to increase the speed with which those molecules are traveling, right? So if pressure is fixed, if the number of collisions on the side of the box are fixed, then as we increase the volume, we must increase the temperature, because if the temperature stayed the same, the pressure would drop. So that's why with Charles's law, we have this relationship between volume and temperature. I've just realised there should be an S there. Right, now, there's one final law, and that is called the Gay-Lussac law. Gay-Lussac, discovered by two physicists, Gay and Lussac. And what Gay-Lussac tells us is that if we hold the volume constant, again, so if we're keeping this gas in exactly the same volume, then the pressure is proportional to the temperature. And from everything we've said before, this one should really seem obvious, right? Because you're keeping the box in the same size. You're keeping the gas in the same size of box. So if you're increasing the temperature there, that is, if you're increasing the speed with which the molecules are traveling, then of course you're going to increase the pressure, because as the molecules are traveling faster, then they are hitting the side of the box more often because they're traveling at a greater speed. So we have these three laws here: Boyle's law, Charles's law, and the Gay-Lussac law. And all of these are holding one variable constant and noting how the other variables interrelate to each other. So at constant temperature, we have pressure is inversely proportional to volume. At constant pressure, we have volume is proportional to temperature. And at constant volume, we have pressure is proportional to temperature. Now, all is left to do is to combine these three laws, right? So if we bring all of these three laws together, then what we have is pressure times volume is proportional to temperature. And we're basically there now. So what does proportional mean? Well, if A is proportional to B, that means that A is equal to some constant K multiplied by B. That's all that proportionality means. So we have PV is equal to some constant, which I'll write little c, times T. And as it turns out, that constant of proportionality is equal to N, which is the number of molecules in our system, multiplied by K subscript B, which is the Boltzmann constant, multiplied by T. So PV is equal to NKBT. And that is the ideal gas law. Now, it might seem that I pulled this constant of proportionality out of nowhere, but when we get to a later stage, when we have a bit more kinetic theory of gases, we'll see where this comes from. So that is the ideal gas law. And we have a few different things to say at this stage, right? So firstly, this works on what are called ideal gases. Now, the word ideal is doing a lot of groundwork there. So firstly, we're assuming that all the molecules in this gas are point particles. They have zero volume. That's quite an important assumption, might not always be correct. Secondly, we are assuming that there are no intermolecular forces, that these things essentially never interact with one another. That's another important assumption, not always correct. And thirdly, we're also assuming that these molecules are moving classically. That is, we're not accounting for relativity in any sense here. And a lot of molecules are moving at speeds almost at the speed of light, so relativity actually plays a very big role. But nevertheless, this law is incredibly accurate in many, many different scenarios. And especially when it comes to thermal systems like engines. And remember, thermal physics was developed in large part, especially in the early days, to account for the behavior of heat engines and stuff like that. So this is a really good law, and it's incredibly, incredibly useful, and it comes up again and again and again. And the kind of things we can do with this law and discover with this law are really, really vast, and is a brilliant law to remember. If you're only going to remember one equation in thermal physics, let this be the one. So there you have the ideal gas law. What we're going to do in the next video is come back to how we deal with such large systems of particles, because what we're going to do moving forward is actually start to dive into making predictions about these things. So we need to cover combinatorial problems on how we can actually make formulas and start to talk about such large numbers of things. We're also going to look at Stirling's formula, which is a brilliant formula which we'll use again and again and again, and it's very appropriate when you're dealing with vast systems. So we're going to look at a few examples of combinatorial problems, and we might even do a derivation of Stirling's formula, because it's a really beautiful piece of maths and it's not too complicated and it's quite nice to see, even if you don't necessarily need to remember exactly how it's derived. So yeah, I think that's everything. See you next time.